Hello, today we're continuing in our series on nuclear physics looking at alpha particle decay. This really follows on from the nuclear fission and radioactivity video earlier in the nuclear physics playlist. Just to recap, when scientists were studying radioactivity, they found that there were three types of decay particles, and they could be categorized on the basis of how they responded when placed in an electric field. So if you take two plates, one positive, one negatively charged, and you shoot the particles between the two plates, what you found was that there were one set of particles that veered towards the positive plate, and they were called the beta particles, which meant they had to be negatively charged. There was one set of particles which veered toward the negative plate. They were called alpha particles, so they had to be positively charged. And there was a set of particles that didn't veer at all. They went straight ahead, and they were called gamma particles, which meant that they wouldn't have any charge at all. We now know that an alpha particle is just a helium nucleus. So take the electrons off, and a helium nucleus is 2 protons and 2 neutrons. So it's 2 protons and 4 nucleons. A beta particle is nothing more than our old friend the electron, and a gamma particle is in fact, of course, electromagnetic radiation. It's the very high frequency end of the electromagnetic spectrum. It's even higher in frequency than X-rays, and therefore pretty dangerous. And if we remind ourselves of the reasons for decay, which we set out in the video on the semi-empirical mass formula, if we plot our old friend the neutron versus proton chart, here is a line that is neutrons equals protons. That's just a line to guide the eye. What you find is that for small a, for small numbers of nucleons, indeed the number of neutrons does indeed equal the number of protons. But as you get to higher a values, the stability line diverts, so that in a stable nucleus there are more neutrons than there are protons. And we showed the reason for that in the semi-empirical mass formula video. And any nucleus that forms on this line will be stable. It doesn't decay. But around this line there was a group of nuclei which are unstable and which will want to decay to become stable. So let's take a nucleus above the line and a nucleus below the line. A nucleus that's above the line decays kind of in a southeasterly direction onto the line. In other words, it goes down 1 neutron but up 1 proton. So in other words, 1 neutron becomes a proton. A neutron becomes a proton plus an electron plus an anti-electron neutrino. On the other hand, a nuclei that is below the line will decay upwards to the stability line. That's in a sort of northwesterly direction, and that means going up a neutron but down a proton. So in other words, a proton is converted to a neutron plus a positron plus an electron neutrino. And that is beta decay. In other words, electrons and positrons, which we'll come to in the next video. For this video, we're concerned with the top end of this process, where energetically, instead of converting neutrons to protons or vice versa, it becomes energetically favourable just to kick an alpha particle out of the nucleus. In other words, you lose 2 protons and 2 neutrons in one fell swoop. So if you take any element in the high end of this chart, we'll call it X. It will have Z protons and A nucleons in all. That will decay to a new element Y with Z minus 2 and A minus 4, and that will be the new nucleus, plus an alpha particle with 2 protons and 4 nucleons in all. That's 2 protons, 2 neutrons. And the reason that decay happens is that the mass energy on this side of the equation is greater than the total mass energy on that side of the equation. And consequently, nature, which always wants to find the lowest energy point, will happily decay because this has higher energy than this does. So if a high energy decays to a lower energy state, it gives off energy. So there's one other thing to put into that formula, Q. Q is the energy that is released. And how is that energy released? In what form? How does it manifest itself? It manifests itself as kinetic energy to the two daughter particles. This is the parent. These you might regard as the daughters, the products, and this Q is shared as kinetic energy between the two. Now the question is, does this decay happen instantaneously? Do all X's become Y's in a fraction of a second, giving off alpha particles and energy? No, they don't. There are varying rates at which this change takes place. So we better just remind ourselves of how you calculate what that rate might be. And you'll remember we have done this before, so I'm just rehearsing this. You can say that the number of decays per second is going to be proportional to the total number of nuclei that you have. That makes sense. The more nuclei you have, the more decays you're likely to get. And the number of decays per second can actually be written mathematically as dN by dt, the rate of change of nucleons with time. Or the rate of change of nucleus with time. The number of N is the number of nuclei that have not yet decayed. So the rate of change of those with time is going to be proportional to N, and that is going to be equal therefore to lambda N, where lambda is now just a decay constant. It's a constant. And I'm going to put a minus sign in front of the lambda because, of course, what dN by dt is doing is decreasing the number of nuclei, not increasing them. So if it was an increase, if n were increasing, then dN by dt would be lambda n. If you are decreasing the number of nuclei, then it's dN by t is minus lambda n. So we can rearrange that to say that dN over n is equal to minus lambda dt. And now we integrate on both sides. The integral of 1 over n is, of course, log to the base en, and that is equal to minus lambda t plus, of course, the constant of integration. And now we kind of anti-log both sides. So you now get n on that side and you get e to the minus lambda t plus c on this side, which is equal to e to the minus lambda t times e to the c. Those are, of course, one and the same thing. Now, what is this e to the c? Well, let's just explore what happens when t is 0. That is to say, right at the start of the process. Well, at the time you start, n will be n naught. That is the number of nuclei you start with at time t equals 0. And that's going to be equal to e to the minus lambda t. Well, t is 0, so that's e to the 0, which is just 1, times e to the c. So now we know what n naught is. It's e to the c. So we can now rewrite this equation as n is equal to n naught e to the minus lambda t. And if you divide both sides by n naught, you get n over n naught is equal to e to the minus lambda t. Now what happens when n over n naught is a half? That is to say that n is now half the number of nuclei you started with. So 1 over n naught is a half. That's going to be e to the minus lambda t. And I'll put a little half down there. It means that's the half-life. The time it takes for the number of nuclei to reduce to half its original level. Well, let's turn both sides of the equation upside down. That will give that 2 is equal to e to the lambda t to the half. And now let's log both sides. That means that you get log to the base e of 2 is equal to lambda t to the half, which means that t to the half is log to the base e of 2 divided by lambda. And that is the formula that enables you to calculate the half-life That is the time it takes for half the number of nuclei to decay. Log to the base E of 2 is, I think, about 0.6 something. So obviously as lambda increases, as the decay constant increases, the half-life will decrease. So if you plot the number of nuclei undecayed against time, and you start with, let's say, n0 at time t equals 0, and let's say these are 10-second intervals, and let's say the half-life is 10 seconds, what that means is that after 10 seconds you'll have half of what you had before. So you'll have half of n0. Does that mean that after 20 seconds you don't have anything at all? No, it means that after 20 seconds, in other words after a further 10 seconds, you have half what you had at the beginning of that time period. And then at the next 10 seconds, i.e. at 30 seconds, you'll have half of what you had at 20 seconds, because the half-life is every 10 seconds. Every 10 seconds you halve what you had at the beginning of that 10-second slot. So you get half again here. So you're never going to get to 0 because you're always going to go down to half what you had before. So the decay line looks something like that. Every 10 seconds, if that's the half-life, you have half what you had at the beginning of that 10-second period. So let's look again at our alpha decay. What we're saying is that an element X with Z protons and A nucleons will decay into an element Y with Z minus 2 protons, A minus 4 nucleons, plus our alpha particle, which is just our helium nucleus. And of course you also get energy because the mass energy of this was greater than the mass energy of this, and so there's a surplus of energy. That comes out in the form of kinetic energy shared between the two products that are made. So if we think about X being classically a stationary nucleus, if you like, and then it decays, it gives off an alpha particle here, which will have kinetic energy, because that Q is going to be shared between the two. So it's got kinetic energy, which means it's moving. Kinetic energy, remember, is half mv squared. So it's going to have mass, well, we know that, but it's also going to have velocity. So it's shooting off in this direction, which means that the Y particle must go in that direction. Why? Because momentum must be conserved. The momentum of Y must equal the momentum of the alpha particle. The original momentum of X was 0. We're assuming it wasn't moving classically. So if the alpha particle comes off in one direction with a certain velocity and a certain energy, it must follow that the Y nucleus must now go off in the opposite direction so that the magnitudes of the momentum are exactly equal. And since Py equals P alpha, we'll just call that P. Now the total kinetic energy of the two particles is Q. So Q is the total kinetic energy. What is the kinetic energy of the alpha particle? Well, kinetic energy is half mv squared, but that can also be written as p squared over 2m. P, remember, is momentum, that's mass times velocity. If you square that, m squared v squared divided by 2m equals half mv squared. So the kinetic energy of the alpha particle will be the kinetic energy of the momentum of the alpha particle squared divided by 2m alpha, where m alpha is the mass of the alpha particle, plus the kinetic energy of the Y nucleus, which is Py squared divided by 2my, where my is the mass of the Y nucleus. And since Py equals P alpha equals P, this is simply P squared over 2 into 1 over m alpha plus 1 over my. And if we make a common denominator out of that, we get that Q is equal to P squared over 2 into, make the common denominator m alpha times my, should be a capital Y of course, and then above you've got my plus m alpha. Now let's rearrange that for P squared. So P squared is going to bring the 2 up there, you get 2Q into, now you just obviously have to tip this upside down, m alpha my over my plus m alpha. So what is now the kinetic, and remember P is the momentum of the y, and it's also equal to the momentum of the alpha particle because their magnitudes are the same. They have to be. We argued that. So what is the kinetic energy of the alpha particle? Well, it's going to be p squared divided by 2m alpha. P squared is this, so that's going to be, well, the 2's will cancel. So you're going to get q into this term divided by m alpha. So the m alpha will cancel and you get my divided by my plus m alpha. That's the kinetic energy of the alpha particle. Now let's suppose that we started with x, and let's say that A is 200. We are, after all, talking about the high end of the NZ diagram. That's where alpha decay takes place, where the total number of nucleons in a nucleus might be of the order of 200. And that's obviously going to produce Y, which will have 196 nucleons, plus the alpha particle, which has 4. So very roughly, these are the atomic weights of these atoms, 200, 196 and 4. So now we can substitute in this formula here. So the kinetic energy of the alpha particle is going to be Q times my, which is 196, over my plus m alpha, which is 200, which means that 98% of the total output energy goes in kinetic energy to the alpha particle, and obviously only 2% of that energy goes to the Y nucleus. So for all practical purposes, the alpha particle is carrying away nearly all of the energy that is generated by that decay. And I just want you to notice one other thing that we'll need when we come to the next video looking at beta decay, that if the mass of the alpha particle were very much less, let's say it were the mass of an electron, then you would have my over my plus a very, very, very small amount. That would be 99.99%. So if the alpha particle had the mass of an electron, it would carry away 99.99% of the energy. So the alpha particle carries away about 98%. The electron, if the alpha particle had the mass of an electron, that would carry away nearly all the energy. So now let's establish why that decay does not happen instantaneously. Why does it have a half-life? Why does it take time? And why does it take varying amounts of time? Well, let's consider the nucleus. And remember, this is a large nucleus of the order of A greater than 150, because that's where alpha decay tends to take place. So you've got 150 nucleons, protons and neutrons, surging about inside this nucleus. And what we're going to assume is that there is a preformed alpha particle inside the nucleus with 2 protons and 2 neutrons. So you've got a preformed alpha particle which is just jiggling about inside the nucleus and moving about. And eventually it gets towards the edge of the nucleus, and of course what we want it to do is to come out. Why then doesn't it do that, and why doesn't it do that pretty sharpish? Well, we need to look and see what the potentials are that are operating. So we need the old famous potential diagram. Here is the potential, and this is distance x, if you like. Now we know that inside the nucleus there is an attractive potential, the nuclear potential, which we have hitherto represented as a square well. It's not, but it'll do for our purposes. So inside here, which is the equivalent of being inside the nucleus, the helium particle, or the alpha particle, is bound. It's attracted. So inside we know that that alpha particle, because it's got the 2 protons and 2 neutrons, will be held inside the nucleus. But that is only up to a distance of r, where r is, of course, the radius of the nucleus. We are thinking classically here, of course. What happens beyond the radius of the nucleus? Nucleus do not, of course, suddenly end. There is a fuzzy region where the nuclear force tails off. We represent it as a square well where there is no tail off, it just suddenly stops. But that will do. What happens beyond that? Well, beyond that, you've got the Coulomb potential, because the alpha particle is positively charged and the nucleus is positively charged. So you've got two positively charged, as it were, units which are going to repel. So there's going to be a Coulomb force, and that's going to give rise to a Coulomb potential, and that Coulomb potential is a 1 over r potential. The force, of course, is a 1 over r squared term, but the potential, and that's what we're plotting here, is 1 over r. Now, once it gets within this radius here, the nuclear potential is greater than the Coulomb potential. Consequently, that's why the nucleons, or at least certainly the protons, don't fly apart, because what's holding them together is greater than what's trying to push them apart. But outside the realms of the nuclear force, then the Coulomb potential is a repulsive force, and therefore you've got this potential described here. Now Q, which is pretty much the kinetic energy of the alpha particle, is, let's say, this value here. And this value here we're going to call Vc. It's the value of the Coulomb potential at the radius of the nucleus. Now if you've got an alpha particle inside the nucleus, that's this region here, we'll call this region 1, that's okay, because the alpha particle is preformed inside the nucleus where the nuclear force is holding everything together. So no problem. If we ignore this a little bit here and we come to region 3, that's okay, because the energy of the alpha particle is greater than the potential energy of the Coulomb field. So that's all right. But what about this little region here, which I'm going to call region 2? The problem is the alpha particle can never get into region 2 because it hasn't got enough energy to get over this Coulomb potential barrier. So although it would be all right when it got to region 3, it can never get to region 3 because it can't get through region 2. So since it starts in region 1, i.e. inside the nucleus, it looks as though classically it is forced forever to remain in the nucleus because it just can't get over the Coulomb barrier at the radius of the nucleus. How then is the alpha particle to ever get out? Well, we've been talking classically, and of course we shouldn't. We have to talk quantum mechanically, and that means we have to resort to Schrödinger's wave equation. So we're going to apply Schrödinger's wave equation to this region, region 2, where classically the alpha particle cannot go. So let's just remind ourselves of the time-independent Schrödinger equation, which is minus h bar squared over 2m d2 psi by dx squared plus v psi equals e psi, where psi is the wave function, representing in this case the alpha particle, and that's the time-independent Schrödinger equation. Now we can always just generally rearrange this to say that d2 psi by dx squared is equal to minus 2m over h bar squared into e minus v times psi. That's still the general form of the time-independent Schrödinger equation, but just rearranged by moving this term over to this side, bringing the v over, so it becomes minus v, and that is that. Now for region 2, what is E? Well, E is the value of the energy of the alpha particle, which is Q. Okay, it's 98% of Q, but let's not trouble ourselves with that. It's pretty much Q. What is V? It's the value of the Coulomb potential, Vc. So for region 2, we can rewrite this equation as d2 psi by dx squared is equal to minus 2m over h bar squared into Q, because Q is now E, minus Vc times psi. Now Q minus Vc is always going to be a negative term because Q is less than Vc. That's the whole point. If Q were greater than Vc, there wouldn't be a problem. You could get out. But if Q is less than Vc, then you can't get out. So that's a negative term. And if Q minus Vc is a negative term, then that minus term there will make it positive. So this whole term here is positive. And that means you can write that d2 psi by dx squared is equal to k squared psi, where k squared is this entire term here. The reason we need it to be positive is that if k squared equals this, then k will be a real number, not an imaginary number. And of course we know the solution to this. That means that psi is going to be an exponential term, ae to the plus kr plus be to the minus kr is the solution to this equation. It's not an oscillatory term, it's not simple harmonic motion. That would need a minus sign there. This is an exponential increase or an exponential decrease. So in other words, if we plot the wave function against r or x, I should have put x of course here because we are talking about d2 psi by dx squared, so it's an x term and we're plotting the wave function against x, then this term, the exponential term, would increase like that, and this term, the exponential decrease, would decrease like that. Now what we've always done in the past is to say we can't have that term. In other words, we can't have the exponentially increasing term. Why? Because that tells us that the wave function increases the further away you go. And the wave function squared is a proxy for the probability of finding the particle. So if this term were true, then when a nucleus decays, the most probable place for finding the alpha particle that emerges would be on the other side of the universe. The further away you can go, the more probable it is that you'd find it, which is obviously a nonsense. This is obviously the right term, because the further away you go, the smaller the wave function, and therefore the smaller the wave function squared, and therefore the smaller the probability of finding the particle. The further away you go, the less likely you are to find the particle. So that makes sense. But this, let me remind you, is the wave function in region 2, the region where classically the alpha particle cannot go. So in region 2, we have that psi is equal to be to the minus kx. And that means that, remember, let's redraw that diagram of the three regions. In region 1, we had a nuclear potential, and then we had a Coulomb potential. There was the value of Q, and this is region 1. This is region 2, and then beyond that is region 3. We're talking about region 2 where the alpha particle can't classically go. What we're saying is that in that region, and only in that region, because we haven't worked out the wave function for 1 or 3, we've only worked it out for 2. In that region, we've got a wave function which decays exponentially. Now, what is going to be the shape of that exponential decay? Well, this is an e to the minus kx decay, and you'll remember that k squared was equal to minus 2m over h bar squared q minus vc. That was k squared, remember? So this shape is going to be heavily influenced by the difference between q and vc. The greater that difference, the sharper is going to be the fall off. So if q is a long way short of vc, then the exponential decay will be very fast. If q is almost vc, then the exponential decay is going to be very gradual. So the greater this gap is, the sharper the exponential fall will be. So if I just draw that a little bit bigger, remember this is region 2, the region where classically the alpha particle can't go. If q is almost vc, you get a very gradual fall off. But if q is a long way short of vc, then the fall off is very fast indeed. Now what does that mean? Well, let's look at this point of region 2. I mean, this fall off is never going to go to 0. It's just going to progressively, exponentially get smaller. Indeed, let's look at this point here, right at the edge of region 2, as it is about to get into region 3. This wave function is very, very small, but it's not 0. It's small. And if there is a wave function, then there's a wave function squared. And what do we know about the wave function squared? It's the probability of finding the particle at that point. So in quantum mechanics terms, what this says is that even though classically there is no way that alpha particle can get into this region, if there's a wave function in this region, then there is a probability that the particle can be in this region. And consequently, since it can get all the way to, as it were, the edge of region 2 and on the cusp of region 3, the alpha particle can move through region 2 because there's a positive wave function throughout, and the wave function squared is probability. So, what this alpha particle does, instead of going over the barrier, which it cannot do, it tunnels through the barrier. And that is called quantum tunneling. And that's the way it works, that the wave function has a value in the region where classically the alpha particle is forbidden. But you can see that the probability of it being here is very small. So what is actually happening is that as here we are with the nucleus again, and here's the preformed alpha particle, as it approaches the edge of the nucleus and wants to come out, it's subject to a kind of probability test. There's a very low probability that it will get into region 2 because there's a very low value of the wave function. So it's almost like you get to the edge of the nucleus and you throw a dice. And if you get a 6, you can go out, but if you get any of the other numbers, you can't. Except that the dice will have different numbers of sides. A dice might have 1,000,000 sides. And only if you throw a 6 can you get out. If you throw any of the other million numbers, you can't. And the number of, as it were, the number of sides the dice is allowed to have is determined by just how low the probability is. And that will be determined by just how great Q is compared to VC. If Q is almost the value of VC, then the value of the wave function will be high, the probability will be high, and consequently the alpha particle will come out very quickly. If Q is very much lower than VC, then the probability is very low and the alpha particle will take a long time to come out. And just how different that is can be quite staggering. If we plot, and this is experimental results here, we're plotting the half-life of alpha decay against the energy of the alpha particle, which is, for all intents and purposes, Q. And we'll call this 4 MeV, 6 MeV, 8 MeV, 10 MeV. These are typically the values of the energy of emerging alpha particles from alpha particle decay. If the energy is 4 MeV, then typically the half-life for 4 MeV alpha particle is of the order of 10 to the 17 seconds, which is broadly equivalent to 10 to the 10 years, which is broadly the age of the universe. The age of the universe is about 13.7 billion years, so 10 to the 10 is 10 billion years. So if you've got 4 MeV, which means you're quite a long way short of the Coulomb potential, the alpha particle has a very, very small probability of getting through that region 2, and it's 10 to the 10 years for the number of nuclei to decay to half its original level. On the other hand, if the alpha particle has 10 MeV on emergence, then the half-life is likely to be of the order of 10 to the minus 7 seconds, a 10 millionth of a second. So you can see that this scale is logarithmic because we've got 24 orders of magnitude here, 10 to the minus 7 seconds, right up to 10 to the 17 seconds. And all of that is influenced by what is actually a very narrow energy range. But the problem is, you see, that the Coulomb potential, minus 10, is a small value. Consequently, the probability, the value of the wave function is high, and the probability is high of emergence. So very short half-life. The Coulomb potential -4 is a very large number, so the probability, the wave function is very small, the probability is very small, so the half-life is very long. From which we conclude that the energy of the emerging alpha particle is proportional to 1 over t to the half. T half-life. As Q increases, as Q gets bigger, the half-life gets smaller. And then finally, let's just look at what happens to the states of these nuclei when alpha particles are emitted. This is an energy scale. This is the X nucleus, and let us say it's an even nucleus, and it's in the ground state of 0+, so it's a 0+ ground state. When that decays, it will produce a lower energy Y nucleus, also in its ground state, and that will also be 0+, because if you lose 2 protons and 2 neutrons from an even nucleus, you get another even nucleus. That's lower energy because that's the whole point. When alpha particle decay takes place, it's because the products have a lower energy, a lower mass energy than the originating product. So Y has obviously got to be a lower energy than X. So effectively the decay takes you from X to Y with the emergence of an alpha particle. Now, what is the angular momentum of that alpha particle? Well, it has to be L equals 0, because you go from an angular momentum state of 0 to an angular momentum state of 0. There was no change in our angular momentum. Therefore, the angular momentum of the alpha particle in this set of circumstances has to be 0. But of course, that isn't the only route. Once again, we're looking at energy increasing, and we'll start with X in the ground state 0+, and here is Y. This is the 0+ ground state, but let's suppose it had a 2+ excited state. Then, in theory, at any rate, the X nucleus could decay to an excited state of the Y nucleus. And if it did that with the emergence of an alpha particle, you're now going from an angular momentum of 0 to an angular momentum of 2, which means, of course, the alpha particle must itself carry away an angular momentum of 2 in order to balance the angular momentum of the 2 nuclei. But if you remember from the video we did on the collective model, when we were talking about rotational nuclei, we looked at the classical sense and we considered rigid rotating objects. And we said that they have an energy, and that energy is equal to L into L plus 1 h bar squared over 2I, where, well, actually this would be it would normally be L squared, the angular momentum squared. But in quantum mechanics terms, L squared, the operator, is L into L plus 1. So the energy would be L into L plus 1 h bar squared over 2I. And where I is the moment of inertia. This was all done in the video on the collective model, looking at rotational nuclei. My point here is to say that if L is not 0, then this is an additional energy term which, as it were, adds to the height of the Coulomb barrier, so it makes it even higher, which reduces the probability of the transition taking place. So ordinarily, though there are exceptions to this, ordinarily falling to a value of L greater than 0 will actually be probabilistically less likely. Now, there are circumstances, I have to say, why that will happen quite often, but generally speaking, you've got this additional energy barrier that will stop it from happening. So generally in these circumstances, the 0 to 0 decay, the 0 plus to the 0 plus decay, is far more likely, because the 0 to the 2 plus decay requires an angular momentum, and that angular momentum will add to the energy that you have to overcome, and thus make the probability of the alpha particle tunneling through that region too much less likely. Finally, let me just explore this option. Here once again is X in the 0 plus ground state. Here is Y. This is the 0 plus ground state. Suppose it had a 2 minus excited state. Could there even be, no matter how low a probability, could there be a decay to the 2 minus state? Well, you might say, yes, there could. The emerging alpha particle would have L equals 2. But look, L equals 2 means that the parity has to be positive. We've shown that before. I should put that above there. Parity has to be positive. As we've shown before, L equals 0.2468 means parity is positive. L is 13579, parity is negative. But you're going from a plus to a minus state. Parity can't be positive in those circumstances. So parity couldn't be properly conserved. So no nucleus will ever decay from the 0 plus state to the 2 minus state for alpha particle decay. That is forbidden.